Okay, so continuing on in our examination of horizontal asymptotes and limits at infinity, I wanted to say one more thing. We've got this conceptual arithmetic that we can use. We have a new technique that we use, and this is really the preferred method. But sometimes it's good to just have an idea of what's happening before you actually go for the limit. And so let's take a look at what happens if you take the limit as x goes to infinity of a polynomial divided by a polynomial. And the first case will be where we have the degrees are equal. Okay, so for example, let's take the limit as x goes to infinity of x to the fourth plus x squared minus 2 divided by 3x to the fourth plus x squared plus 5. Oh, let's say x cubed. Good. Alright, so the way to think about this, if you just want an intuitive understanding of what's happening, is you want to take the leading term of the denominator and the leading term of the numerator and just look at that. So what we would say is, intuitively, this is going to be behaves like the limit as x goes to infinity of x to the fourth over 3x to the fourth. And so notice that those are going to, the x to the fourths go away and you're left with 1/3. So we expect to see that the limit is 1/3, but now you do want to go back and show formally that the limit is 1/3 by dividing the numerator and denominator by x to the fourth and then continuing with the algebraic version. But it is nice to know what you're heading towards there. So that's why I say we can use a little bit of intuition on these just to get a good sense of what's happening. Okay, so what happens then if the degree of the denominator is bigger than the degree of the numerator? So for example, suppose we're taking the limit as x goes to infinity of x squared minus 1 divided by x cubed. Well, there's two ways to do this when we say we're going to divide by our x to the n. Well, maybe I should use the intuition first. Intuitively, what's happening? Leading term over leading term would give us x squared over x cubed, which is 1 over x. And so as x goes to infinity, this is going to go to 0. And so therefore we expect to see this limit going to 0. And in fact, that is what happens. Now you can either divide top and bottom by x squared or x cubed. X cubed might be easier, because if you do that, then the top just becomes 1 over x minus 1 over x cubed divided by 1. And so you're getting 0 divided by 1, which is 0. Good. Alright. Finally, if the degree, you can probably guess what's going to happen in the next case. Degree of the numerator is bigger than the degree of the denominator. Right, so if you have, let's just reverse these from the last one. What happens if you have x cubed divided by x squared minus 1? So again, you could just divide top and bottom by maybe by x squared in this case. I guess you could divide top and bottom by x cubed, but then you'd have this 1 over x, you'd have a 0 in the denominator, and you don't want a 0 in the denominator. So I wouldn't divide by x squared then, or x cubed, but we could divide by x squared. So x squared over x squared. I keep forgetting to do the intuition here. What happens if you do the intuitive version? X cubed over x squared is the limit as x goes to infinity of just x which is, just as you guessed, infinity. Good. So in this case we get the limit as x goes to infinity of x over x squared is 1 minus 1 over x squared. And so the numerator then is going to, getting infinitely large, the denominator is just going to 1. So then altogether we do get that infinite limit. Good. Okay. So it is good to try out a little bit of what am I trying to say? Intuition. So how about this? Oh, let's do a harder one. It's not a polynomial. How would you think about the limit as x goes to infinity of the cosine of x divided by natural log of x? So go ahead and pause if you want a minute to think about it. Are you back? So the way to think about that is that cosine is a bounded function. It's going to be between plus or minus 1 no matter what the x value is. But what happens in the denominator? This is getting arbitrarily large, going to infinity. Right? And so even though the numerator is oscillating, the denominator is getting huge. And so overall then, what's the system going to be doing? I believe it's going to be going to 0. Can we prove that? Oh, I think we can. So let's see if we can show that. Cosine of x divided by natural log of x. We're going to do just exactly what we said. The top function would be 1 over the natural log of x. Bottom function is minus 1 over the natural log of x. Right? And now if you take the limit as x goes to infinity, does this setup look familiar to you? This is going to 0, this is going to 0, so therefore by the Squeeze Theorem, that's going to 0. But geometrically, let's double check what we're doing here. So what we're saying is we have this upper function that's going to a number, and the bottom function is going to the same number as x goes to infinity. And so then the unknown function that you're trying to take the limit of is stuck in between, right? And so this limit, the Squeeze theorem will work for infinity as well as for a number. Okay. Okay, we got one more example, and this one may be a little bit tricky. Examples. These are actually two examples. We want to take the limit as x goes to infinity of the square root of 2x squared plus 1 divided by 3x minus 5, and then we're going to take the limit as x goes to minus infinity of the square root of 2x squared plus 1 divided by 3x minus 5. Okay. Now, when we talked about intuition, right, we said that as x goes to infinity, right, this is going to be behaving like the square root of 2x squared divided by 3x, right? That's the leading term over the leading term, which would be the square root of 2 times x over 3x. And so you could cancel those, and this is what you expect to come out, right? And indeed, that is what happens if you divide the top and bottom by x. We get the limit as x goes to infinity of the square root of 2x squared plus 1 divided by x squared. If you bring the x into the radical sign, then you have 3x minus 5 over x in the denominator. Just continuing that through, in the numerator we have the square root of 2 plus 1 over x squared now, divided by 3 minus 5 over x. Good. And now we're ready to take the limit. This goes to 0, that goes to 0, and so we are left with the square root of 2 over 3. Very good. Now, here's the big question. What changes would be made if we're going to minus infinity instead of positive infinity? Do you see any changes here that would have to happen? You might pause it for a second and think about it. Are you ready? Here's the change. If x is greater than 0, then it is true that you can replace x by the square root of x squared. But if x is a negative number, that is no longer the case. Then x is actually minus the square root of x squared. And this is the reason for that is because as soon as you take x squared, right, your number becomes positive, and then you take the positive root, and so to make x negative again, you have to multiply it by a negative 1. So did you see where we used that over here in this example? It was right here in the intuition, and it was right here in the algebra. So let's see how that works if you're going to minus infinity instead of positive infinity. So we'll rewrite the expression down here. So we're going to take the limit, oops, sorry, let's go back to white again. The limit as x goes to minus infinity of the square root of 2x squared plus 1. My pen is going crazy. 3x minus 5 equals the limit as x goes to minus infinity. I'm going to divide top and bottom by x. But now when I bring it into the radical sign, I'm replacing x by minus the square root of x squared. Okay, so this is my reasoning here. And now the same algebra occurs. I'm going to end up with minus the square root of 2 plus 1 over x squared divided by 3 minus 5 over x, and so I'll have minus square root of 2 over 3. Good. Okay, so that's probably the trickiest case in this section. So go ahead and try some of the algebra out, and yeah, I think we'll try to do a few more examples maybe. Well, I think I'll wait, and we can do examples together if you want to set up a time to meet. Okay, I'll talk to you later.